Everyone say hi.
What's going on, Sam?
I don't think they're that excited.
Wait, can they hear it?
We're going to return to a type of graph that you guys looked at the first day that we talked about limits. So this particular one shows a lot of gaps. It shows a lot of asymptotes. Connor, some notes? You've got these. Okay. Any case, as x approaches 6, we're going to start to introduce this idea of an exponent next to this. I showed this a couple of times, but this is a limit from a single side rather than a limit from both sides. So this is saying specifically, what is the limit as x approaches 6 when we say from the right? So traveling from the right side, coming in from the right. So move your pencil or wherever your eyes are to where x is equal to 6. And look what the limit is approaching from the right. Not going the direction right, but approaching from the right, or on the right side. That limit, as we approach 6, 6 is right here. Yep, it's not down there, it's up here, would be what? Well, shoot. We have an ordered pair 2, 4, and we have an ordered pair 7, 0. And I need to be 100% clear on where that is happening and what this is. So let's build the equation of the line. I'm going to do a point-slope form. Y minus 0 equals, 4 over negative 5, x minus 7. And, it's 4/5. As I plug in 1 for x, I get y of 1 is equal to 4/5. So knowing that this ordered pair right here is the ordered pair 6 4/5, we can say that that limit is 4/5. Now, as you approach 6 from the left, so now we're going to start moving and approaching 6 from the left side. What do we get? The same thing, because we're on a continuous line here. So I also get 4/5. And then finally, what's the limit as we approach negative 6, which is different than approaching 6 from the left side? Yeah, the limit is 0. Here's negative 6, and the limit as I approach from the left is equal to the limit as I approach from the right. That is 0. Okay. Let's talk about negative 10. What's the limit as we approach negative 10 from the left? It doesn't exist. We can describe it. Negative infinity. The type of does not exist, but it's a description, so it helps. Limit as we approach negative 10 from the right. Same thing. And when the left-sided limit and the right-sided limit are the same thing, then we can describe the limit as we approach negative 10 without a plus or minus as just the same thing. They're all three descriptions, but this tells you more than just saying does not exist. It tells you that you're approaching from the same direction. So it gives you a little bit more info, which is good. Okay, let's do some function values. What is f of negative 3? I'll let you find that ordered pair. It is negative 3. It's right here. What is f of 2? 4. That's where the closed circle is. What is f of 5? Nope, we got the equation. We just did the equation, right? Plug in 5 for x. 5 minus 7, negative 2 times 4 over negative 5. Don't you get 8/5? Okay, let's look at 9. What's the limit as x approaches 9 from the right? Negative. 9 from the left? Positive. And limit as x approaches 9 without positive negative. We have to say does not exist. And so if you're consistent in your usage of positive and negative infinity, then when you finally do write does not exist, you actually do mean a split. So it gives you more information about that. Okay. The next question says, for what values of c does the right-sided limit not exist? So we're going to ignore any, well, let's not ignore. Let's look at positive, negative infinities and include those. So let's kind of just keep traveling along the graph and see where does the limit not exist. So I'd argue negative 10, oops, I should put that up here. Negative 10, the limit doesn't exist because it's a negative infinity style. 9 it wouldn't because it's also an infinity style. But is there anywhere else where the right-sided limit does not exist? No, the right limit exists. The right limit exists and the left limit exists at x equals 2. What's different about that is that they're different from each other. Let's examine this here for a second. Does it make sense to you that the limit as x approaches 2 from the right of f of x is equal to 4? And here the limit as x approaches 2 from the left of f of x is equal to, what would this be? And so the limit as x approaches 2 of f of x would be what? Since the limit as we approach from the right is 4, and the limit as we approach from the left is negative 3, then what's the limit as x approaches 2? Nope, doesn't exist. They are not the same, so we have to say the limit does not exist. Probably a little bit more excitedly. Are we getting to the point where people haven't seen that movie? Yeah. Ouch. Mr. Keelahan used to watch Mean Girls as a class after the AP exam. Okay, next. What values of C is f of x continuous? This is going to bring back our definition of continuity that I want to now introduce for the second time. 3 conditions. Condition number 1. To be continuous at C, the limit as x approaches C, it's glitching, x approaches C from the right of f of x has to be equal, try to get an arrow in there, has to be equal to the limit as x approaches C from the left of f of x, which is to say the limit exists. 2, f of C exists, which is just to say that there has to be a closed circle or something there. There can't be nothing there. So that's the second condition. And the third condition is that the limit as x approaches C of f of x is the same as the function value. Strictly speaking, you could probably summarize this whole thing down to the third condition, because by saying that they're equal to each other, you're kind of implying that they both exist. But it does give you a nice little checklist to check. So we're going to do this in interval notation. I want to go back up to the graph and tell me on an interval, we'll start with negative infinity. Tell me the first place you get to where the graph is not continuous. Well, this is also a great little visual tool, because for those of you who like sketching and drawing and sketching lots of things out, you can take your pencil on the graph and try to sketch the graph left to right. And anytime you have to lift your pencil, you have a point of discontinuity or a place of discontinuity. So as I travel from negative infinity, where's my first x value that has discontinuity? Negative 10. So we're going to go from negative infinity to negative 10 and on an interval. And then let's keep going. Negative 10 to where? Negative 6. Negative 6, the limit's there, but it's not continuous at that point because the function value doesn't exist. Okay, now keep going. Okay, negative 6 to 2. And then we go from 2 to and then we go from 9 to infinity. Okay. To where? Oh, shoot. Oh, dang. We have to put closed negative 12 to 12s on these, don't we? Because at the very top it said that. Oh, Miguel, you got me. Yeah. It does, but we're going to include 12 and negative 12, and here's why. Endpoints of a closed interval, we count those points as continuous. That's just a kind of qualifying rule, and I want to write that up here. Endpoints of closed intervals are themselves continuous, because it doesn't make sense to talk about a limit from a side of a graph that doesn't exist. It just gets a little silly there. I also want to mention one other thing, and this came up in a calculus chat room bulletin board thing that some of the people still look at, and that's this. Strictly speaking, there's a whole argument going on about whether I can use the union symbol with intervals like this, or whether that's actually mathematically incorrect to do so. I'm not going to be picky about this. There are people who are starting to be. Because what you're saying is the graph is continuous on these intervals together collectively, which means that I should be able to trace everything in there as one single continuous piece. And they're saying the proper way to do it is not to use the union symbol, because they're not unified together as one continuous piece. It's to actually truly separate them out and say it's continuous here, and then it's continuous here, and then it's continuous here. And I just roll my eyes and say, okay, whatever. Yes, commas. We'll honor the chat because, okay, fine. We'll just kind of scratch out the unions just so you can see this is the moment where we were paying attention to that and somebody raised a stink about this. This is going to become more applicable when we talk about increasing, decreasing regions, because they got all picky about, well, it's not increasing on a union because it's not increasing all throughout the whole thing. It's two different people. Okay, whatever. Okay, next, flip it over. You guys can graph the piecewise function. Don't wait for me on this. Go. Drop.
Ready.
Are you?
Of course.
So 2x minus 1 when x is less than negative 1. I just plug negative 1 in and get negative 3. Open circle. Slope of 2 is just going to put me right down there. It's not looking very straight, so we'll do that. That looks better. Then negative 1 from negative 1 to 1. And then x when x is greater than 1. So you guys remember when I was picky about drawing half points?
Yeah, it was cool.
Was it really? Is it the most horrible thing to happen to you?
Of course.
Okay. And we get this. The graph is there just as a visual tool. You actually should be able to answer these questions without the graph and just by looking at the piecewise. So I want you to try to do that and use the graph as just a visual aid. For instance, as we approach negative 1 from the left, what I'm truly looking at is this piece right here. Approaching negative 1 from the left is just a substitution. I should get negative 3. Approaching negative 1 from the right actually means I'm plugging it in here, because that's the piece that I'm approaching from the right side. It should also be negative 1. And then as I approach negative 1, neither from the left or from the right, I have to say does not exist, because the two of them are not the same point. Okay. What about negative 10 from the left? Negative 10 times 2 minus 1, we are looking at this piece here. So negative 21, which is kind of fun because it's in a part that you can't see, but you know that the left and the right side should be the same because this is in a line segment. So I know that negative 10 from the right should also be negative 21. Okay, 16 does not apply to the graph. New question. So I want you to read this and tell me what you think here. Just start putting things down. If a vertical asymptote of the function occurs at x equals c, then the limit can only equal one of three things. Vertical asymptote wherever the x value is c, just at this place. You're not saying that there is a point there. I'm not saying that c is a point on the graph. I'm just saying at this particular c value. So what are the three possibilities? Infinity? And does not exist. And since we're having fun with this, can you guys next to it put like a little sketch of what they look like? Right. Or you can do them with your hands. You do like that, right? And then like that, and then this or this. Since I really want to be complete, I'm going to flip it around and do it the other way for the does not exist. And then since I really, really want to be complete, I'm going to put dotted lines in for the vertical asymptotes because I'm just that cool. Okay. Yeah, it's glitching. Connor, you think I've made the case for JD to upgrade me to a 16 gigabyte RAM computer? He'd do it?
I mean, I think
2.5 years before this is due for its upgrade.
maybe.
It is. Would you argue that of any teacher that needs it, though? Probably me.
I mean, yeah.
And to anyone that does it. You guys keep going. I'll eventually get down to it when this computer decides it's thought enough and can restore me back to the visuals of this. We're not done, are we? Yeah, there's 17. I want you to actually read this. This is a question type you guys should love or not love. Actually, my students generally don't love these kinds of questions. You're given the following information about a function f of x. First things first, all 5 of these points are about the same graph. Okay? It's saying that as x approaches -2 from the left, the limit is -infinity. As x approaches -2, the limit does not exist. As x approaches -2 from the right, f of x is positive infinity. -2 from the left is infinity, and f of 0 is 0. Based on the above, answer the following. What are the equations of the vertical asymptotes? Where are they? And x equals 2. You don't unless you're talking about a one-sided limit. It's possible there might not be graph there, so that's actually telling you that there's actually graph on the other side. The limit as x approaches 2 from the right of f of x. What do we know? Two from the left is infinity. So what about 2 from the right? Well, we could say it could be infinity, could be negative infinity, or could be does not exist. You guys get to pick which of those it is. Does not exist. Oh, it wouldn't be does not exist. It could be because if there's no graph there. Like that's an option just to not sketch anything. Yeah, from the left it's positive infinity. So just to be difficult, I'll pick that one in my sketch. Because the next one is to make a sketch. There's more than one correct answer. So we're going to draw just a graph of what this could look like. Start with the thing you know for sure that everyone has to have. Roman numeral 5. F of 0 is 0. Drew, where am I putting point? Putting it at the origin. And then we said we have vertical asymptotes at x equals -2 and x equals +2. And as I approach 2 from the right, I get a positive infinity, and 2 from the left, I get a positive infinity. It's not truly a parabola, but you can draw it like that. Parabolas do not approach asymptotes. Remember, they expand infinitely far left and right. But just keep your sketch simple. As we approach from the left, I can have something like that. That makes the split happen. And you're welcome to put whatever you want to on the right. Do you know what I would put if I wanted to keep the does not exist? That I put? Like if I wanted to make this match here, what would I actually draw? Yeah, nothing. I'd leave it. I would leave it exactly as it is. Now the limit from the right does not exist because there is nothing from the right. Okay. You guys know enough about symmetry to know that the logical completion of this graph would probably include that, right? It's really difficult to get a piece that just mathematically does not include the right but does include the left. So, but our piecewise can be whatever we want. Okay, 18, almost there. At least that's what Tiana said. Let f of x equal these two, and I want to find a value that the limit at x equals 4 exists, or the limit as x approaches 4. This is a lot easier than it actually looks. What? Yep, plug in 4 here and plug in 4 here, and what do the two of them have to be? Yeah, they have to be the same thing. I'm trying to find cx squared minus 2cx. I want that to equal c root x plus 4 at x equals 4. Because if this limit's going to exist, it has to be the same from both sides, so they have to converge at the same point. We can plug in 4, so I get 16c minus 8c, and I need that equal to 2c plus 2. 16 minus 8 minus 2 is 6c equals 2, and I get c is equal to 1/3. Then finally, we have your favorite types of questions from geometry. They are good. If the limit is equal to infinity, then x equals 4 is a vertical asymptote. That is always. If the limit exists, then the f of x is continuous at that place. That's a sometimes. Let's talk about the place where it's not. This is how it could potentially not be continuous. This is also how the limit could exist and it not be continuous. Both of those are cases where it's continuous, or sorry, where the limit exists. I'll put on these. Limit exists, but not continuous. In either of those, you'd have to lift your pencil up. In the first case, the limit and the function value are not the same. In the second case, the function value doesn't even exist, but the limit exists. And lastly, number 21, the limit as x approaches 4 of 3 is 3. That's an always. That's just a basic property of limits. We're saying as x approaches 4, what's the y value of the line y equals 3? It's going to be 3 everywhere. Okay. Stop.